Hi, this is lecture 21 of M.223. Okay, so till now what we have done is the notion of differentiability in last few lectures. Before that we have seen notion of continuity. Before that we have seen the notion of sequence in R. So SR is a notation for set of all sequence in R. Then we have said in this collection set of all sequence in R, we have said some are special. There are some special class of sequences. So what are those? One is bounded sequences, then we have monotone sequences, then we have convergence sequences, then we have Cauchy sequences. So in this session we will see another interesting class of sequences in R, which I am calling as summable sequence. The reason why I am saying I am calling is this is not a standard notation, at least not when we are dealing with a sequence in R. It is used for some other purpose in some advanced course, but one can still use. I mean, this makes sense. This notion of this phrase summable sequence makes sense when we are talking about sequence in R. So just like the previous interesting classes, this means it is a sequence. Of course, we are talking about summable sequence. This is a sequence and it has something to do with sum, addition operation on R, in R. So a sequence A from N to R is said to be summable sequence if something happens. That something should depend on addition property of R. In R we have this addition. So how do we define that? Given a sequence, given this sequence A, we assign a new sequence that I am denoting by SA, a sequence from N to R. For each n belongs to N, I am assigning an element in R. I am saying it is summable. So it is expected that what I am going to write here has something to do with sum, the addition of some elements in R. So here for each n, I am adding first n elements of this sequence, that is the definition, not n, I is equal to 1 to n ai. I am taking first n elements of the sequence A and adding them. That is what I am denoting as SA. This sequence SA defined in this way. For each n, the real number that we are defining is this. Now what is summable? If this sequence is convergent, if SA is convergent, then we are calling, then we will call A to a summable sequence, not SA. For this sequence we have considered a new sequence. If this is convergent, then we will call this to be summable sequence. This may be slightly confusing. There are two sequences and we are talking about convergence. So it is not very clear whether we are talking about convergence of this or convergence of this. Maybe in a few minutes it will be clear that convergence of this does not really mean anything. I mean, you will come to know what I mean here. So given a sequence A, the corresponding sequence, if it is convergent, then we are calling A to a summable sequence. This has also a name. This SA is called sequence of partial sums. This is the standard name. This is a standard name. So it is called sequence of partial sums. If this is convergent, we are calling it to be summable sequence. Now whenever we talk about convergence, unlike Cauchy property, whenever we talk about convergence, there is some element L to which this converges. So here SA should converge to something. That limit we are denoting by this symbol AN n is equal to 1 to infinity. So, this symbol means it is a limit of sequence of partial sums associated to this sequence A that I started with. See, and this is called as series associated to the sequence A. See, there is a possibility of getting some confusion here. This symbol does not mean sequence, it means its limit of a sequence. So, series is limit of a sequence if it exists. So, you need to see the difference that this is a sequence, from the sequence we produce other sequence SA of partial sequence of partial sums. Then if this is convergent, then the limit of that we are calling as series. So, you should not get confused that this is not a sequence, this is a series, this is a single element. A sequence cannot be single element, right. So, this thing is an element of R, it is an element in R. Now, and as I said, this is called a series associated to the sequence A. By abuse of notation, people write this, people including me, people write this even before we check that this is convergent or not. So, we write this and we will write something before and after, something like check if this is convergent or not, which means check if this corresponding sequence of partial sums is convergent or not. So, we write this symbol even before we check the even before we know the convergence of this sequence SA. So, as I said, this separately does not have any meaning unless we know that it is convergent. So, we will add something before and after. So, we will say the series converges or the series diverges or check if the series converges or diverges. So, we do not use this separately, we use this with the previous phrases. Yeah, we will try to keep it consistent, maybe somewhere I will mess up, but I will try to follow that follow what I have said just now. This ideally should be used only as the limit of some sequence, but but people use, including me, use this without even knowing that it makes sense. So, that is why we use this phrase, check if the series converges or diverges. So, this phrase the series converges means this is coming from some sequence of partial sums SA. So, this phrase the series converges means the corresponding sequence converges. Similarly, the series diverge means the corresponding sequence diverges. As I said, this is not a sequence. So, this is slightly misleading, but this is the standard notation that people are using from long time. Maybe we need to change it sometime, but I do not know an appropriate alternative, so I am just following that. Ideally, this phrase is slightly confusing when we are dealing with already sequences. This is used for sequences. It is positive in some, it is helping in some sense. It is saying this phrase says some sequence converge. What is the sequence? That is sequence of partial sums, and this thing, if it converges, is the limit of that sequence of partial sums. Now, assuming you understood to some extent what is happening here, let us try to do some example. So, given a sequence A, let us try to produce a sequence of partial sums first. Say SA, what is it? Let us start with a very basic example. This A, let us take it to be the identity sequence, everything is going to 1. Let me write this clearly. N goes to 1 for every n belongs to n. This is a very simple sequence. So, for this at least the corresponding thing should converge. I mean, this is a very basic thing. So, whatever we are going to do here, it should work nicely for at least this kind of sequences. So let us check that. So n goes to where? N goes to as I said, for each n the element that we are assigning is sum of first n elements of this sequence. Here everything is 1, so you would not have to think so much, you are just adding 1 n times, so that is simply n. So this is what? This is n. So the corresponding sequence of partial sums is just the sequence n. Something is not okay here. This sequence is not convergent, right? Even for this kind of very simple example, the sequence of partial sums, this is not convergent, this is not bounded, you already know that. So this should not make you feel unhappy. This should tell you that whenever we are trying to work with series, very basic examples might fail. So it is a positive thing, believe me, it is not a negative thing. So for this kind of simple sequence, the sequence of partial sums is not convergent. So one cannot talk about this notation does not make sense, 1 plus 1 plus 1 this dots. This does not have any meaning according to whatever I have said till now. Okay, so now we need to ask the following question. Okay, at least for this kind of very simple sequences, the SA is not convergent. So are there really any sequences A for which this is convergent? That is the basic question. Are there any examples at all, or we are doing just for time pass? So before that, see, this is one strategy that we usually follow. We are looking for examples of sequences for which SA converge. So let us try the other way. Let us start with some arbitrary sequence and assume that this is convergent. Then one might get some idea about this sequence. That is the strategy, and then we can put the condition on this and then see whether this is convergent or not. So let us take a sequence AN and assume that this series converge. I am using this for yeah. So this series converge. What does it mean? That the corresponding sequence of partial sums is convergent. SA, maybe I will write n here to denote the nth element. This is convergent. And see, observe that here we are concerned about just the convergence, not really the limit point. We are not mentioning anywhere. So now we will use the property that this is convergent and try to conclude that some result about this sequence AN. So let us assume that SAN converges to L, and then see whether we can say anything about this sequence AN. So what do we have? Given epsilon positive, there is n belongs to n, such that for every n greater than or equal to n, we have what? SAN minus L is less than epsilon. And what is this? This is summation of I is equal to 1 to n AI minus L is less than epsilon. It is not very clear, how do I even proceed? Suppose this is an integer, I might have tried integer and it is equal to something, I do not know how to proceed here from here. That is because this AI and L may not be related at all, that is the problem. So let us change the starting point. Instead of writing this L, let us use a Cauchy property. There L does not occur, so here maybe we will be able to do it more easily. So let us use the Cauchy property. What is it? The same thing, even epsilon positive, there is n belongs to n, such that for every n comma m greater than n, what we have is this. and so I should replace this L with what? I will just polish it. Summation I is equal to 1 to m ai. So whenever I am saying here m comma n greater than n, either m greater than n or n greater than m, and both of them should be greater than this capital N. So I am assuming that m is or n is greater than m. If n is equal to m, then we may not really conclude anything. I mean it's true for any n comma m. So in particular for n greater than m, it should hold. Now what is this? This is the summation I is equal to 1 to, okay, I am collecting first n terms and then removing first m terms, m is less than n. So I am removing this. So what I am left with is the remaining m minus n terms. So what should I write here? N plus 1 to m ai is less than epsilon. Suppose, oh sorry, this is m plus 1 to n, this is n, this is m plus 1, I have said here n is greater than m. So this says some result about the sum of some elements of the sequence. So if this is true for any m comma n, it is true when m plus 1 is equal to n. See I am doing this because then there will not be many elements here, there will be only one element, right. If I am taking sum from m plus 1 to n and m plus 1 is equal to n, then there is only one element. What is it? This is in this case this is just mod a n. This is true for every n greater than or equal to n. Now you know what is happening here. Given epsilon positive, there is n belongs to n such that whenever n is greater than or equal to n, mod a n is less than epsilon. What does this mean to you? This says the sequence a n converges to 0. So this is the first result that we have seen. Suppose we are given a sequence a n such that the corresponding series a n is convergent, then the sequence that we have started with should be convergent and converge to 0. See, there are two things. One is it should be convergent, so one cannot take any arbitrary sequence to start with. Then it should converge to 0. So obviously we should not have we cannot take this sequence. This is convergent of course, but to 0, not this converges to 1, not to 0. So that is the problem. We could not prove that this is convergent. So now what is the result that we have? I have already mentioned here. For any sequence a n, if the corresponding series is convergent, then this sequence should go to 0. So now that we are comfortable with I am assuming we are comfortable with using this notation. So this is what I will be using, this phrase. For a sequence a n, this is convergent or this is divergent, that is what we will use. This abuse of notation, but still we will use for this makes life easier for me, not for the students. They might get confused, but we have a lecture notes, so you can just go back and check. There I will add more details. So given a sequence a n, if this is convergent, if the series is convergent, which means what? The sequence of partial terms is convergent, then this sequence that we are starting with should be convergent to 0. Yeah, as I said, we got some information about the sequence a n, knowing that this series is convergent. Now one can ask, okay, suppose I have a sequence a n and that goes to 0, do I know if the series is convergent or not? N is equal to 1 to infinity, this is convergent, right? That is what I said before. We are looking for a condition on this sequence a n such that this is convergent. What we have is, when we tried to check in the opposite direction, this convergence implied that this sequence goes to 0. So we are just using, I mean, to what extent this is really sufficient. If n goes to 0, do I know if this is convergent or not. That is what we are trying to see. Maybe we may not be able to prove for a general statement, that this we may not be able to prove even if this is correct. So as the first step, let us check with the sequence that goes to 0 and see whether the sum is convergent or not. As I said many times, the only sequence that I know that goes to 0 is 1 by n. Are their cousins, n square, n cube and all that. So 1 by n goes to 0. Let us check if summation 1 by n is equal to 1 to infinity is convergent or not. This is what we are trying to see. So the first thing that we should do is we should look at a sequence of partial sums. So S1 is just 1, S2 is 1 plus 1 by 2, S3 is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, S4 is 1, oh sorry, it's only 1 by 3, 1 by 2 plus 1 by 3 plus 1 by 4. And if I write further than this, then the time will be devoted only to writing this down. But observe the following, that so we are trying to see if Sn is convergent or not. That is what we are trying to see. So before looking, as I said, before looking at convergence of any sequence, it is useful, may not be sufficient, but it is useful to know that the sequence is bounded. So it may be useful to know that Sn is bounded or not. So we will try to approximate this sequence with some other sequence. So now what we do is the following. Observe that 1 by 3 is greater than 1 by 4. 1 by 4 is equal to 1 by 4, and this I am leaving as it is. So 1 plus 1 by 2. So S4 is greater than or equal to this. I mean, suddenly why I am doing this? That's what you will come to know. I am trying to approximate this sequence. The nice thing here is, I mean, the reason why I am doing this is the following, that 1 by 4 plus 1 by 4 is 1 by 2, and I already have this 1 by 2 here. So this is equal to 1 plus 1 by 2 plus 1 by 2, that is equal to 1 plus 2 times 1 by 2. Maybe if we try for a general element, we will come to know what is happening here. So S4 is greater than 1 plus 2 times 1 by 2. The strategy that we have used here is the following. We are taking the first two elements, we are leaving as it is. The next two elements, 1 plus 3, 1 by 3 and 1 by 4, both of them are greater than 1 by 4, and we got this approximation. So let us check for 1 by S5, 1 by 5, these three, I do not really know how to use it. I mean, for these two I am using already 1 by 4. So for 1 by 5, I do not know what to use. So let us write for 1 by 6 also. So let me 1 plus 1 by 2, 1 by 3, 1 by 4 plus 1 by 5. This we are leaving as it is. For these two we are writing as 1 by 2. This is separate, I do not know what to do for that. So let us see whether we can do something when we write 1 by 6. It is not very clear what to do here also. 1 by 7, I do not know what to do. 1 by 8. Yeah, this is a nice point. Now what we are doing here is the following. Each of these elements, 1 by 5, 1 by 6, 1 by 7, 1 by 8, all these 4 elements are greater than 1 by 8, right. So we will use, now what is this? This is S8. So we could not do anything, we could not say anything about S5, S6, S7. S8 we could we are able to do, we are trying to say something. So S8 is greater than or equal to 1 plus 1 by 2, these two I am writing as 1 by 2 again, plus these 4 are greater than 1 by 8 or equal to 1 by 8. So 4 times 1 by 8, so this is what 4, yeah, this is, so these are at 1 by 2 only. This is equal to 1 plus 1, 2, 3, 3 times 1 by 2. Observe the pattern here. S2 2 cube is greater than or equal to 1 plus 3 times 1 by 2. More generally, we have S 2 power n is greater than or equal to 1 plus n times 1 by 2. See, I am not saying this you should understand this in the first attempt, it may take some time, but this kind of tricks you should get used to, it will be useful. This is what I am supposed to teach you in real analysis, how do you approximate some sequence or some series or something else. This is what I am supposed to do, to teach you how to approximate some sequence. So now observe that see this sequence 1 plus n times 1 by 2, this is divergent, right? If it is convergent, this means what? This is inverse constant, this means this is convergent, which means what? The sequence n is convergent. So this sequence 1 plus n times 1 by 2, this sequence is not convergent, right? And these elements are greater than this. So by what property? You think about the name. By some property, it says this sequence is divergent. Yes, 2 power n is not convergent. See, observe, we could not say anything really about the whole sequence Sn, but we can say that there is a subsequence of the sequence Sn for which is not convergent. What does this say? This says Sn cannot be convergent, right? I have told you before also, suppose I have a sequence and if I know it is convergent, then for every subsequence it is convergent, it converges to the same element. This is used as a negative result in the sense this result is used to say some sequence is not convergent. How do we do that? Given a sequence, we somehow produce a subsequence that is not convergent. So by previous result, if I take the corresponding opposite segment, it implies the sequence An is not convergent. So here we could not say anything about the sequence Sn, but we can say we could say that S2n is not convergent. It is a subsequence of this sequence. Is it a subsequence? Check for yourself. You know what is the definition of subsequence, and you know what is you know the description here. So check for yourself that this is subsequence of this, and by the reason that I said just now, this Sn is not convergent. So this sum 1 by n is equal to 1 to infinity, this series is not convergent. So this symbol does not really make any sense. That's what we conclude. Okay, till now what we have seen is that we saw the notion of series. What does it mean to a series associated to sequence? Then we have seen what does it mean to say it is convergent. Series convergence means the corresponding sequence of partial is convergent. That's what you should remember and understand. Then we have seen that suppose we are starting with the sequence and we take the corresponding series and we know that it is convergent, then we could say that the sequence An that we are starting with is convergent and that goes to 0. Before that what we have seen is that we took the constant sequence 1, it is convergent, very nice sequence, but the corresponding series is not convergent. This was the problem. So that is why we were checking to get some condition on the sequence An, if I know summation An is convergent. So that gave the result that summation An convergent implies An goes to 0. Then what we have done, then hoping that it is sufficient, we were trying to see that 1 by n goes to 0 implies, does it imply summation 1 by n? I mean this is a true statement, 1 by n goes to 0. Then for this sequence, do we know whether this is convergent or not? That's what we were trying to check, and then we realized that this is not true. Summation 1 by n is not convergent. This is not convergent. Now there are other sequences that goes to 0. As I said, 1 by n square, 1 by n cube. Maybe they may be convergent or not convergent. If this is convergent, then we would have got some hope that 1 by n square, 1 by n cube, n power 4 may be convergent. But now the first step itself we got a negative result. Now I am slightly afraid to proceed further using this sequence, using this kind of sequence. So before that, proceeding to n square and n cube, let us do a simpler example. See, we don't know other examples of sequences that goes to 0. What are those? One is the one sequence that is 1 by n goes to 0 and 1 by n power m or n square, 1 by n cube, so on. There is other class of sequences that goes to 0 that we know. If I take some element L belongs to R with L less than 1 or mod L less than 1, then we know L power n goes to 0. Observe the difference between these two. So, for example, what we have, suppose L is equal to 1 by 2, then we are talking about 1 by 2 to the power n, this goes to 0. Now one can ask whether summation 1 by 2 power n, whether this series converges or not. 1 by 3, 1 by 4, 1 by 50 something. So for any element L, here I am taking only positive elements. For negative elements also one can use a similar thing. Now let us check this. This may be, see, this may be not very easier than doing this, but because we got some failure here, we didn't get what we wanted, so we are leaving it for some time. We will go back to that again. So we are doing something else just to get some positive idea. So that's what we are doing here. Other sequence that goes to 0 that we know is this kind of sequences. L belongs to R, mod L less than 1, L power n goes to 0. Now what? So we are checking whether this is convergent or not. So what is the sequence of partial sums? Yes, n is what? L plus L square plus so on. See, I am assuming L is positive just to be comfortable. To L power n, that is the sequence is defined as L square so on. So Sn, sum of first n elements, is just this L plus L square plus so on, L power n. Now what? I don't even know how to proceed. So the first thing that should come to your mind is there a other description for this sum? There are so many components here, so can I rewrite this in other terms? This is where the usual binomial theorem comes to help. What is 1 minus L square? This is 1 plus L times 1 minus L. 1 minus L cube, 1 minus L times, maybe it is it is the strategy to write 1 minus here and plus here. What is it? 1 plus L plus L square. I think you know what to write next. 1 minus L power n is equal to 1 minus L times 1 plus L square so on L power n minus 1, n minus 1. See the difference. It is 2 here, it is 3 here, it is 1 here, it is 2 here. So 1 minus L power n is equal to 1 minus L times 1 plus L square plus so on plus L power n minus 1. Is it useful for us? That is the question. There is some common part. This is not same thing as this, but just with one is missing here, but everything else is same. N minus 1 is here, but there is n here. Then you can change it to n plus 1. Then you will get n here. I mean, if you are really concerned about that kind of thing. So what I have is the following: 1 minus L power n plus 1 by 1 minus L is equal to 1 plus L plus so on L power n. Now we only want this part, we do not want this part. Whenever you do not want something and there is addition, you click it to the left side, you get a minus 1. So we have minus 1 plus this thing is equal to L plus so on. Now this is slightly better than this description. I mean those two are equal, but it is easy to see. Now what do we have? Sn is equal to minus 1 plus 1 by 1 minus L minus L power n plus 1 by 1 minus L. What is the use of looking at in this form? Nth term, that means this here in the sequence of partial terms is this, and I hope you are already seeing the nice thing that is happening here. This part, there are only 3 parts. For any n, there are only 3 parts. That is the first nice thing. Here we have n parts. For each n we have n parts. So just looking at that we get some disturbed. So here we have only 3 parts. For each n there are only 3 parts. This part is constant, no problem. This part is also constant, no problem. This part depends on n, but as I said, n goes to because L is less than 1, L power n goes to 0. In particular, this sequence L power n plus 1 sequence. So what is the difference between L power n and L plus 1? L power n sequence start with L power n plus 1 sequence start with L square. That is only difference. So this also this goes to 0. So that says what? Sn converges to minus 1 plus 1 by 1 minus L minus 0. Right, this convergence should not make a difference here. So this is I am writing as it is. This goes to 0. There is a 1 minus L part, that is constant. So constant times 0 is 0. So this is 0. So this limit, let me write down this as a is equal to this. So this is 0. So I am removing this. So what do we have? Minus 1 plus L plus 1 by 1 minus L. This is L by 1 minus L. Now this formula, this you might have seen before already, but you might not know how to prove. Now we have seen the proof also. So given an element L belongs to R positive such that L is less than 1, 0 less than L less than 1, it is already saying here, then for the sequence Ln, this is already going to 0. So there is a I mean it makes sense to ask for convergence of this element, this series. Then we got a positive result here, unlike the 1 by n, which was we kept so many hopes on that, but we could not prove that. We proved the opposite thing. We proved that it is not convergent. But here we got a positive result. We got that it is convergent, and we got the limit also. I mean convergence means it should come with a limit. And what is the limit? It is L by 1 minus L. This is the limit of that sequence. See, it is always useful to have at least one positive result. Maybe previously also, suppose we have a continuous function, then we know how to produce more continuous functions. Just put some constant before that. Suppose f is continuous, then 2f is continuous, 3f is continuous, 4f is continuous, nf is continuous, or alpha f is continuous for every alpha belongs to R. So just one example of the positive thing, it gives some hope that maybe one can produce more convergence series from just this, or using this we may be able to prove that some other sequence is convergent. There are two purposes. One is to produce more series that are convergent. The second purpose is we can use this idea to prove some arbitrary series is convergent. You will come to see more about that. Okay. So now we got, as I said, now we got some example that is positive. We will try to use this to check convergence some other series. So suppose we have 3 sequences an, bn, cn, such that we have this condition, and an is convergent, cn is convergent, both of them are converging to same element L, then bn is convergent, converges to L. Right? This is a result about this is what we are calling as squeezing theorem for sequences. Now see, it is not special about I mean in particular, if we are dealing with sequence of partial sums, then still it is hold, right? Say SA or SB, SC. See, this is true for any sequences. In particular, for sequence A, B, C, for these three sequences, let these three denote the corresponding sequence of partial sums. Then, if this is the case, then and this are converging to same element, say L, then this should come to the same element, right? What does this mean? This being convergent means what? Summation an n is equal to 1 to infinity converges, summation n is equal to 1 to infinity Cn convergent. This implies summation n is equal to 1 to infinity Bn is convergent. So this kind of see this should tell you something that whatever we have we know for limit of sequences, right? Of course, series is the limit of a sequence of partial sums. So whatever we know for the whatever results that we know for limits of sequences, we can just copy paste here, maybe with a slight care, and conclude something about the corresponding series convergence. Right, so here we have the following. Suppose we have three series, summation an, summation bn, summation cn, and an is less than or equal to bn less than or equal to cn, and I know that this is convergent, then this is convergent. This kind of small thing we can really this may be useful at a later stage. Now I just now said that we can use the idea from limits to say something about series. They are particular case of limits of some sequence. For example, we do know that if an converges to some L, Bn converges to some L prime, then an plus bn converges to L plus L prime. In particular, in the following case, where this A is a sequence of partial sums associated to the sequence A, and this B is the sequence of partial sums associated to the sequence B. Suppose they are convergent, then the sum, it is not an plus bn, here it is corresponding SAN, SBn, the corresponding sum is converges to just this sum. What does it mean to say this is convergent? It means the series summation an n is equal to 1 to infinity, this is convergent. This says what? Summation n is equal to 1 to infinity bn is convergent. So this combines to say that summation an plus bn is convergent, and this limit is equal to just the sum. Right, this should tell you that we are really just copy pasting the idea from limits of sequences and putting here, and it seems to work. And not just that, given a sequence that goes to L, if I take if I take some other constant and just simply multiply that, it will still be convergent, but not to L, maybe to alpha. So one can do the same thing here also. Suppose we have a sequence an, we multiply that by some element alpha, non-zero zero doesn't really matter. Then if it is convergent, then alpha times is also convergent, and this alpha just simply comes out when we are taking corresponding limit, corresponding convergence. When we are checking for corresponding convergence, the alpha just simply comes out, and that is all for this session. You can check for yourself whether you can. This is an exercise. What results about sequence of limits of sequences? What results can we just copy paste here to say something about this series? That's an interesting exercise. Check for yourself, and that's all for this session. In the next session, we will see some. See, here we have seen one result that gives some idea that about what kind of sequences can converge, what kind of sequences. What kind of series associated to some sequence converge. If summation A is convergent, then for sure we should have summation n should go to 0. But n goes to 0 doesn't really imply summation is convergent. So in next session we will see some test to check convergence of series. Yeah, that's all. See you in next session.